Hello everyone, and welcome to this video on section 3.2 called Trigonometric Integrals. All right, in this video, we're taking you through a sample version of of a Newton Alta assignment for this section 3.2 on trigonometric integrals. And please be aware that all the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But I'm hoping that they're similar enough, right? The objectives should be the same. The types of problems you see should be the same. So I'm hoping they're similar enough that watching me do these here will help you out in some way when you go and do it yourself. All right, so in the upper left corner, right, you're going to have the title without the word preview. Then in the upper right corner, you have your mastery bar telling you how far along you've gotten, along with an activity log. Shows you each objective and how far along in each objective you've gotten. So it looks like there's only the two objectives here. Then there's a question related to the current objective. And at the bottom of every question, there should be a feedback button where if you're seeing some issues with the problem itself or the answer explanation or some sort of error, please send Newton feedback directly yourself, and perhaps they can fix things. You will not have this instructor cheat button. This is for instructors only. But you should have a more instruction button. So if you're struggling with a particular objective, try clicking on this more instruction button, and it'll take you to a page with some further reading to do or videos to watch or both, and then give you a question related to that reading or videos while the reading or videos are still up. So you can keep referring back to them. And you can work through the assignment that way, every single question if you wish. Okay. All right, so this trigonometric integrals section, again, they talk about, products and powers, integrating products and powers of tangent and secant, also integrating products and powers of sine and cosine. So actually, before I get to this example here, I would like to go over some of the strategy that they're going to instruct you on. And you'll see the strategy also revealed in the answer explanations once we get a couple right here. Well, let's go through the strategies they're going to be teaching you for solving these, for integrating these products of trigonometric functions. All right. So they only break it up into two categories in the two objectives, right? You have the sines and cosines, and then you'll have integrals involving secants and tangents. All right. Because if they went through every possible combination of products of trig functions, there'd be way too many objectives. All right, and yeah, so we're just going to work with the two that they've got here. All right, so first I'll start off with sines and cosines. I'll go over some strategies for doing indefinite integrals or definite integrals, right? But I'll just do the indefinite integrals. Sines and cosines. And then we'll do secants and tangents after that. All right, so first I'll just start off with some simple examples here Let me just go through and work with a few powers of sine. So say, for example, I had the integral of the sine of, and then I'm going to use a to represent a constant here, ax, and then with respect to x, right? Again, I'm going to have a represent just a constant, um, and with sine here, assume it's something that's non-zero, because the sine of 0 would just be 0, and then this integral would be 0, and whatnot. In fact, I'll just say not equal to 0 for the whole thing, for at least these sines and cosines. Now, if it's just sine to the first power like this, right, that should be simple enough, right? The antiderivative of sine would be negative cosine, right? Because remember the derivative of cosine was negative sine, so I need the negative out front to make it positive sine. So it's going to be the cosine of ax. And then to undo the time, if I were to differentiate the cosine of ax, chain rule dictates that I'd have to multiply by the constant, multiply by a. So it would give me this would give me a sine of ax, but I just want one sine of ax, right? So I gotta counteract that by multiplying this by 1 over a. Right? And again, another reason to have the value of a here be non-zero, right? Because I don't want to divide by 0. And then, of course, plus some constant, right? Always with these indefinite integrals, right? So that's for if I had sine to the first. And what I'm going to do is I'm just going to go through powers of sine right now, and eventually we'll get the hang of some strategy here. So another example, if I had the integral of sine squared of, again, say just ax dx here. All right, so for even powers of sine, it's going to be beneficial to use the following identity. And this is going back to whatever trigonometry class you may have had. Hopefully you've come across this identity. If not, be quite beneficial for you to use it now. This is sometimes referred to as a power reducing formula, right? Because this is sine to the second power, sine squared. Well, you might recall that sine squared of, say, theta is half of the quantity 1 minus cosine 2 theta. Right. So you see over here, the power on the trig function is squared, the second power. Over here, it's the first power, this cosine of the first. The only thing, though, is the argument, the angle measure right inside the sine, the input is doubled. And this came from our double angle formula for the cosine. Also, we're going to see this identity come up for when we're integrating even powers of cosine. You could also do this with even powers of cosine, right? Cosine squared theta is 1/2 the quantity 1 plus the cosine of 2 theta. All right, so keep these in mind for when we're looking at even powers of sine and cosine. So I see this even power of sine here. I'm going to rewrite it using this power reducing formula, right? Sine squared of ax is going to be half of the quantity 1 minus the cosine of double this angle. So 2a x, where, if a is a constant, 2a would also be a constant. And then dx, and then of course we can anti-differentiate this. This would be half of integral of 1 with respect to x would just be x, and The integral of negative cosine, would just be negative sine, right? The derivative of sine is cosine. Sine of 2ax. But then don't forget the, times 1 over the constant. This is 2, I'd have to multiply by 2a when I differentiate this, sine of 2ax. So I got to undo that by, multiplying by 1 over 2a. Great. And then, of course, plus any constant. And you can distribute the half here if you want. But yeah, but this is giving me an idea that, when I see sine to some even power, I'm going to be using our sine squared, power reducing formula at some point. All right. Now just one more here with sines, and then I'll just write up a kind of general strategy. What if I had the sine cubed, the integral of sine cubed of ax? Well, the nice thing is odd powers, okay? If I pull one of these sine factors off, so integral of, say, sine squared of ax times the sine of ax, and then times dx. And then recall if you pull one of these off, then the other factor left over will have an even power. Now you can write even powers like this, but I don't see how that would help us here. The reason we're pulling this off, all right, to get this sine of ax dx, all right, to get a sine of ax dx in a differential, I would need to make a substitution for a cosine of ax. All right, the derivative of cosine of ax would involve the opposite of the sine of ax, times a, but it would involve the sine of ax dx on when I do the differential. So another way to rewrite even powers, right, instead of with these power reducing formulas up here, recall this: the cosine, of some angle squared plus the sine of that same angle squared, always equal to 1. So when I'm seeing sine squared, right, so specifically, sine squared, I can always rewrite as 1 minus cosine squared, and vice versa, right? I can write, if I see any cosine squareds, it's going to be rewritten, you could rewrite it as 1 minus sine squared. So notice these are not power reducing, right? There's still the power of 2 and still the same theta inside. It doesn't become double theta. Remember, these were called the Pythagorean identities. All right. Yeah. So this back up here, I'm going to take my sine squared of ax now. After peeling one off, you got an even power. I can rewrite this sine squared in the following way. Sine squared of ax is the same thing as 1 minus cosine squared of ax. Right, that's this here. And then we still have times sine of ax dx. And this is now perfect for a u substitution. Right, so now I make a u sub or a t sub or whatever variable sub you wish, right? Because isn't the derivative of cosine of ax, negative a times the sine of ax, right? So I'm going to let u be replaced by u replace the cosine of ax, right? Just cosine, not cosine squared, just cosine. Every time I see cosine of ax, it's going to be u. And then du, again, will be negative a times the sine of ax times dx here. And you see There's sine AX dx. There's sine AX dx in the integral. Right? So if I were to just divide by, negative a, right, we're going to take our sine AX dx and replace that with, negative 1 over a times du. Right? And then after making these substitutions, now, this here, 1 minus cosine squared of ax, well, that's just 1 minus u squared. And then this rest of it, the sine of ax dx becomes, negative 1 over a, which I'll pull out. That's a constant multiple, constant factor, du. And now I have a simple polynomial in u to integrate. This is just like 1 minus x squared dx or 1 minus t squared dt. So this is negative 1 over a. And then the integral of 1 with respect to u would be u, minus, and then u squared would be 1/3 u cubed. And then, of course, you sub back, right? This isn't a definite integral. I didn't change any limits or anything. So my original integral was in terms of x with respect to x. I need to be back there at the very end. So my integral that I started with then is going to be, negative 1 over a, whatever a is, multiplied by, and then what was u? U was, cosine of ax. So that's, cosine of ax minus 1/3, and then cosine cubed, right? Cosine of ax to the third power. And there we go. And then plus any constant afterwards, right? It's an indefinite integral. But we're doing something like this with an odd power, odd powers of sine. Pull one of them off to make a sine x dx, and then take the even power and rewrite it in terms of cosine and make that substitution. Right, so I think I got the general strategy down for just powers of sine and powers of cosine. All right, powers of cosine would be exactly the same, just switch the functions. So for powers of sine, if I'm doing the integral of the sine of ax to the nth power dx, right? So we saw sine to the first, sine to the second, sine to the cube, sine cubed so far. And let's take n greater than 1, right? Because again, when this is sine to the first, it's very simple. So let's take n greater than 1. We saw that when n is even, so when it was just sine squared or sine to the fourth or sine to the sixth, I'll just say we're going to use those power reducing formulas, right? Sine squared of something, and then bring the powers down. Keep on, and you can keep on doing it, right? If it was sine to the fourth, think of that as sine squared squared, and then you're going to have to do the power reducing thing multiple times, but you keep using the power reducing formulas until you get down to all first powers, and then you should be able to do it, no problem. Maybe we'll come across an example in the homework like that. So I'm going to be using a power reducing formula, right? Sine squared theta equals half of the quantity 1 minus the cosine of 2 theta. And then if n is odd, right, and again, n is greater than 1, so 3, 5, 7, and so on, you're going to rewrite the integrand as, the integral of the sine to the n minus 1 power of ax. You just peel one off, right, times the sine of ax dx, and then somehow, take this, which would have an even power, right? If n is odd, n minus 1 would be even. You're going to use the Pythagorean identity to rewrite this sine to the n minus 1 power in terms of cosine and then make a u substitution. So I'm not going to write all that, but I'm just going to say rewrite in terms of cosine of ax using, the following identity, the fact that, sine squared of something will be 1 minus cosine squared of that same thing. All right. Okay, so that's if you just have powers of sine alone. All right. Now, powers of cosine would be very similar. Powers of just cosine. So again, integral of cosine of some ax, again, a is not 0, ex, to the nth power. And we're going to have n be bigger than 1 because, just plain old cosine should be no problem. And same thing goes if n is even. All right, so if I had cosine squared, cosine to the 4th, 6th, 8th, and so on, keep using those power reducing formulas, right? Say, rewrite cosine squareds as half of 1 plus the cosine of double the angle. And again, if it's cosine to the 4th, you're going to square this, and then you might see some more squares that you have to do it for again, right? You just keep on doing this until you get all down to first powers, and then you could be able to integrate more easily after that. And if n is odd, okay, you got cosine cubed to the 5th to the 7th and so on. Do the same thing. Rewrite as, the integral of cosine to the n minus 1 power, right, times cosine to the first power. And then, this n minus first power should be even. So now I can write this cosine to the n minus first power in terms of sine and then make a substitution because the derivative of sine is cosine and then you should be golden after that. So we write in terms of the sine. And that would be, again, using your Pythagorean identity, right? The fact that cosine squared of something is equal to 1 minus sine squared, right? And then you're going to make some sort of substitution. So this is sine squared theta. So that's if you have powers of sine or powers of cosine separately, right? That's separate. Now, what if there's a product of them, right? So we'll go over the different, I'm just going to write up different strategies. I'm not going to go over all sorts of different examples this time. But now we have, what if we have products of powers of sine and cosine? So I'll just say a product of sines and cosines. So that's the integral of the sine, say the sine of, and we're going to be hoping here that they have the same argument, okay, the same input. So instead of ax and stuff, I'm going to put, theta, and then times some cosine of theta, and then d theta. And again, this will be sine of, say sine to the mth power times cosine to the nth, right? And we go through multiple different cases here. So our cases, first of all, these powers are going to be nice whole numbers, okay? Like fraction powers or whatever, right? Nothing insane yet. So they're either both even, both odd, or one of them's odd. Uh, let's just go if either one of them is odd. So they're both odd or either one of them is odd. So either M is odd, so the power on sine is odd, N is odd, or both. Okay. If this is the case, so let's just say, say M is odd, then just do what we did before, okay? You're gonna have sine, pull one of them off, right? Remember when I talked about having odd powers of sine earlier? So I have sine to the m minus 1 of theta, and then, you got your cosine to the nth of theta, and then that one you pulled off, you throw that at the end, sine theta d theta, and then you can take and rewrite this. This will be sine to an even power, and you can use that Pythagorean identity, right? Say sine squared is 1 minus cosine squared, to rewrite this in terms of cosine, and then you'll have a bunch of cosine and let u be cosine. So rewrite in terms of cosine of theta, in terms of cosine theta, then let u be cosine theta, right? Do a u substitution, and then du would be this sine theta d theta at the end. If n is odd, it's the same thing, just you're going to have u be sine theta. If the power on cosine is odd, again, just pull one off. So you'll have the sine to the nth power of theta, then times cosine to the n minus 1 times cosine to the first, d theta. Again, if you pull one off and n was odd, this is going to be an even power of cosine, this cosine to the n minus 1. And if it's an even power of cosine, you use, cosine squared equals 1 minus sine squared to help you rewrite this in terms of sine, right, in terms of the sine of theta. And then you're going to have a bunch of sines, and the derivative of sine is cosine theta d theta, right? And the du would be negative sine theta d theta, but still up earlier. But then let u be the sine of theta, right? And du would be cosine theta d theta, which I'm seeing here, and you'll get a nice, hopefully easy integral in that case. All right. Now the only other case that really isn't covered here is, well, what if because again, one could be even, the other odd. This one could be odd, the other even, or they're both odd. The only case I haven't covered is what if they're both even. All right. So case 2, both both powers on sine and cosine are even. Right. So this is where those, now you can keep use those power reducing formulas. Right. Remember sine squared equals half. I've written this twice now, of 1 minus the cosine of 2 theta. Right. Cosine squared equals half of 1 plus the cosine of 2 theta. Right. You can just keep doing that for the sine of an even power, cosine of an even power. Get a bunch of cosines, right? You're going to have to multiply stuff out, and then you might see other powers you might need to reduce and integrate and blah, blah. You might even get a mixture of evens and odd powers again. But I would say just, use this to start, use these power reducing formulas to start, and then go from there. It depends on how crazy the powers are. Uh, or, nah, that's good enough. If they have the same power, you know, then you could throw a double angle formula in there somehow, but I would just say that this is good enough, right? All right, so that's your strategies, right? And hopefully we'll bring those back into play later in the assignment for when you have products of sines and cosines. So next part of this, before I even get into the assignment, I want to go over strategy for tangents and secants, right? There's only the two objectives. Tangents and secants. Right, so this time, just to save a little time here, um, I'm not going to do every little individual example, but yeah, let's go powers of tangent first. Then we'll talk about powers of secant, and then the mixture of the two, and the strategies involved. So powers of tangent. So integral of, say, tangent to the nth power of, I'll just use theta now, right? Theta d theta instead of ax, but just something's inside there. So, and again, I'm hoping it's a linear, 2x, 3x, or just x. Now, hopefully you recall the first power. Okay, I'll put that off to the side. This is something you should have been taught in Calculus 1, right? We're in this Calculus 2 stuff in Newton Alta. Remember, this is the natural log of the absolute value of secant theta, and then plus some constant. Or you could say negative natural log of the absolute value of cosine. Right, either one. Right, the derivative of this would be tangent. So that's when n equals 1. Okay. But then after that, not going to have much of a problem. And you know what? Took me about half an hour there to go over the sines and cosines. All right, so you know what I'm going to do instead? All right, I'm sorry. I'm gonna go to the textbook that's being used and show you just the table with the strategy because I really want to just get into the assignment right now. All right, so here we go. All right, here's products of secants and tangents, right? So let me pull this up. All right, now I got it open in another window. Let's go over to that. All right, so here we go. This is from the openstacks.org. Openstacks.org. Calculus Volume 2 text from Section 3.2 called Trigonometric Integrals. So if you're doing an integral of powers of tangent times powers of secant, now they got the kth power and the jth power. I'll just read this off to you real quick here. All right, again, hopefully we can apply some of this. I just really want to get into some of the assignment problems and get through the assignment so this video is not crazy long. I hope you understand. All right, so to integrate power of tangent times power of secant, I use the following strategies. So one, if j is even, all right, so you have an even power of secant, secant squared, secant to the fourth, and it's, of course, a power greater than or equal to 2, pull two of them off. As you might recall, right, the derivative of tangent was secant squared. And you could rewrite secant squared as 1 plus tangent squared, or tangent squared plus 1. So that's the idea here. You peel off the secant squared, and then the other stuff will still be even, right? Because if I pull 2 away from an even power, I'll still have an even power. And then you take that even power of secant, write it as, anytime you rewrite it in terms of tangent using your Pythagorean identities, and then let u be tangent. Do a u substitution, and then du will be secant squared x dx. Second case, if k is odd, so the power on tangent is odd, well, then you can pull one of those off with one of the secants as well to get a secant tangent at the end. And you may recall that the derivative of secant is secant tangent. And if I pull off a 1 from the k, and k was odd, then k minus 1 will be even. And then I can use the identity tangent squared is secant squared minus 1 to rewrite that even power of tangent in terms of secant. So I get a bunch of secants, and then I let u be secant, and du will be secant tangent. Now, if third case, if k is odd, right, where k is greater than or equal to 3 and j is 0. So there's no, so basically odd powers of tangent, all right, for odd powers of tangent, again, you just pull off, see, I pull off tangent squared here, rewrite tangent squared as secant squared minus 1, distribute the tangent to the k minus 2 power, and then you can, you know, integrate the tangent k minus 2 and secant squared no problem by laying u be tangent. And then this tangent to the k minus 2 power, you might have to start over, right? Because it'll still be odd. If I take an odd and subtract 2, it'll still be odd. So you might have to start this over and do the same process again. And then the last case here, if k is even and j is odd, use tangent squared equals secant squared minus 1 to express tangent to the k in terms of secant, right? And then use integration by parts to integrate odd powers of secant. So yeah, when we get to odd powers of secant, all right, they don't write that here. All right, so let me talk one more little thing before we get into the assignment. What do we do with odd powers of secant, right? They talked about odd powers of tangent, but what about odd powers of secant? All right, so one more thing. All right, odd powers of secant, secant cubed, secant to the fifth, and so on. So if I have the integral of, say, just an odd power, secant to the nth power of theta, d theta, where n is odd, and let's say greater than or equal to 3, okay? Because again, the integral of secant on its own is something you should know once again from a calc class. All right, secant to the first power, all right, the integral is the natural log of secant plus tangent, all right, the absolute value of secant theta plus tangent theta, plus some constant, right? So secant to the first power, you should pretty much have down, all right? It's third power, fifth power, and whatnot that I need to do. All right, so here's what you do. I'm going to pull off 2 of these, make this the integral of secant to the n minus 2 power times secant squared. All right, and then we're going to do parts, integration by parts. And what I'm trying to do here is I'm going to create what's called a reduction formula. As if I start off with secant to the nth power, we're going to see I'm going to write this in terms of some lower power of secant, and we could keep using this to lower the power of secant as we integrate. All right, so I'm going to have u be this secant to the n minus 2 power, and then dv be the rest of it, right? Because secant squared is something I know how to integrate. That's just tangent when I integrate that, right? Secant squared theta d theta. All right, and then du, the n minus 2, using the power rule here, times secant, you multiply by the power, then lower the power by 1. So secant to the n minus 3 power theta, and then times the derivative of secant, which is secant tangent, right? Secant theta, tangent theta, d theta. So this is n minus 2 times secant to the n minus 2 power, right? That would add, I got secant to the n minus 3 plus 1, secant to the n minus 2 theta, and then times tangent theta d theta. And then when I integrate the dv statement, right, v would just be tangent of theta, right? The integral of secant squared would be tangent theta. And now I run through my parts formula, right? So this integral of secant to the nth, remember it's u times v. I did this in section 3.1, integration by parts. So it's secant, to the n minus 2 power times tangent to the first power, then minus the integral of v du. So the integral, and n minus 2 can come out of this. So sorry, that's minus the quantity, and that's n minus 2. And then I'd have secant to the n minus 2 power, and then tangent, tangent, making tangent squared d theta. All right, and then if I were to rewrite tangent squared as secant squared minus 1, we get the following. That integral that I started with, secant to the nth, is secant to the n minus 2 times tangent. And then I'll distribute, this is the secant to the n minus 2. I'm going to distribute that over the secant squared minus 1. And then we got minus, n minus 2 times, and then, the integral of secant to the n minus 2 times secant squared, that's secant to the n again. So I got that. And then distributing this here, it'd be minus the integral of secant to the n minus 2. Theta d theta. And do you see over here how this integral here is the same as this one? So I can solve for it. I can get secant to the nth powers integral in terms of, as an expression using secant to the n minus 2. All right, so if I took this minus the quantity n minus 2 and distribute that to both of these integrals here, then I would add it. All right. So if, again, just bear with me till the end here. I'd have minus n minus the quantity n minus 2, and I would add this, so I'd have n minus 2 plus 1. I'd have n minus 1 of these integrals, and minus 1 of the secant to the nth power integral. And then over here I've got the secant to the n minus 2 power times tangent. And then, again, after distributing this minus quantity n minus 2 here, I'd have plus the quantity n minus 2, all right, plus the quantity n minus 2 times the integral of secant to the n minus 2 power. And then finally divide everything by n minus 1. All right. So again, this is called a reduction formula. So the integral of secant to the nth power is everything over here divided by n minus 1. So secant to the n minus 2 times tangent divided by n minus 1 plus, and then n minus 2 divided by n minus 1. I guess you could put the whole thing over n minus 1 as well, times the integral of secant to the n minus 2 power. All right. So I'm going to put this in a box here. All right, sorry for how long that took, but so yeah, this is called a reduction formula. So if I want a power, especially for odd powers, if I want an odd power of secant integral, I just got this here. Just replace n with whatever power is. I got n there, and there, and there, and there. And then here you're integrating to less than that. Right? Your power on the secant is 2 less than that, which will still be odd. And then I can apply the power reduction again to make it even 2 powers smaller. and make it 2 powers smaller until you get down to the first power, right? Because if you have an odd power and you keep subtracting 2, you'll eventually get down to 1. And then you know the integral of secant, right? The integral of secant to the first, right? Here, natural log of secant plus tangent. Okay, so again, you got this here, powers of tangent, powers of secant, all the different cases there. And then when they talk about, the odd powers of secant at the end there, you can go and do this reduction formula over and over again until you get down to the secant for first. So I will bring this back, all right? I will bring this reduction formula back. So I'm just going to set that off to the side here so I can see it still. And I'll keep bringing it back. Okay, so finally, all right, we got the strategies down, and you can keep referring back to them, or go to that section of the text in the OpenStax. Yeah, now let's finally get into the assignment. All right, almost 47 minutes in here, sorry. All right, so first objective I'm looking at, right, solve trigonometric integrals with products and powers of tangent and secant. So what I was just talking about. All right, so here we have the indefinite integral of negative, tangent cubed of 3x. All right, so it is an odd power of tangent. All right, it's an odd power of tangent. So I'm gonna write this down. So we have, the integral of negative, tangent cubed of 3x, and then dx. Now, if you don't like if you want just one thing in here instead of 3x, maybe just theta, you could have that be theta or whatever, but I'm cool with leaving it like that. All right, so I'm gonna pull the minus out here, and the strategy calls for when you have an odd power tangent, pull off. Now I can pull off a tangent squared. Make this tangent of 3x. And then times tangent squared 3x dx. And then rewrite that tangent squared you pulled off as secant squared minus 1. So this is the opposite of the integral of, and then you have the tangent of 3x times, right? And then this tangent squared of 3x, I'm rewriting as secant squared 3x, right? Secant squared of that same argument minus 1. So now we distribute this tangent here. So we'll have minus. Now after distributing the tangent, I'll have two integrals. One integral of the tangent of 3x times secant squared 3x. All right, that integral dx. Distribute the dx too, I guess you could say. And then, minus the integral of just tangent of 3x. Now this integral of just plain old tangent to the first, not a problem. All right. And this one here, I can make a u sub, but again, maybe you see it already. But for this first integral, if I let u, and just for this one, if I let u be the tangent of 3x, then du would be, 3 secant squared of 3x, times 3 though, chain rule dx. And I'm seeing that here, right? Secant squared 3x, so that's going to be 1/3 du. So on the next page, this is minus, This will be the integral of, 1/3. Then I had, u du. All right, u was tangent 3x, and then the secant squared 3x dx is 1/3 du. Then this integral here, right? Remember, this is the integral of the tangent, remember, was the natural log of the absolute value of the secant of, now there is a 3x in here, so I also have to remember to multiply the thing by a third, to counteract the chain rule. But there's that integral, right? So the integral's taken. I don't need the integral symbol, right? That tangent to the first should be known. Right? And now I'm just doing this one still, okay? Now this would be a negative, and then 1/3 times, and the integral of u to u would be half u squared, and then we got the rest of this, right? Say it down here. And what was u? Right? Remember in the integral I had u be tangent of 3x. So I pop that here. This would be negative 1/3 times a half is a sixth, and then u squared from that integral is tangent squared of 3x. And then we have the rest of it, minus 1/3 times the natural log of the absolute value of secant of 3x. And then, of course, plus some constant after it's an indefinite integral. And if you want to distribute that negative that I pulled out earlier, that's fine too. All right, so this is negative 1/6 times tangent squared of 3x, and then plus 1/3 times the natural log of the absolute value of secant of 3x. And then plus some constant, right? There we go. And this is what I'm going to enter back in my calculator. Now, you might recall from section 3.1, there is a way you can check these indefinite integrals on Desmos, right? So if I want, my initial integral was the integral of negative tangent cubed of 3x. So I put in y equals and then I put a definite integral in. And again, you might go back to my section 3.1 video, one of the very first couple examples, where I could set this up. I can define the inverse tangent of, I can not inverse, negative tangent cube 3x dx. This integral from any constant that tangent is defined at. So I'll just go from, say, 0 to x of negative. Now this won't give me a large curve, I don't think, because x, as soon as we pass pi over 2 or pi over 6, this is going to be bad. But we're doing tangent of 3x, to the third power dt. I need a dummy variable in there. I got x in the limits t dt, right? And yeah, notice, right, this is only defined here between, like, probably 0 and pi over 6, 0 and negative pi over 6, but I'm getting this piece of curve, right? So let's focus on this piece here and see if the graph of our result has that same kind of shape between negative pi over 6 and pi over 6, right? So just between here and here, hopefully the graph of our, what we ended up with at the end has the same shape. The negative 1 times, I think I can just put tangent squared like that, of 3x, and then plus 1/3 times the natural log of the absolute value, okay, ABS for absolute value in Desmos, of the secant of 3x, right? And I think all the parentheses are closed there. Yeah, and that's it. Plus, notice if you ignore all the other branches, right? Just kind of zoom in here. Now I could add on any constant I wish, right? Move it up and down plus some c, and then add a slider for c, move this thing up and down, right? But you see this this integral we had, and that had the exact same shape over where that thing was defined when I said it was from 0 to x or whatever, but yeah, they have the exact same shape, just differ by, and they would, and I could, that just tells me right away that my indefinite integral is the correct one. All right. Yeah. So again, you can define your integral in such a way, and then put in what you resulted in, what you said the antiderivative was, and see that those graphs have the same exact shape, right? They just differ by a constant maybe, and that'll tell you like, hey, you got the right idea. Another thing you could do that would take a while, but maybe not so long for this, but differentiate this. Remember, take the derivative of this, and if you get something that's equal to negative tangent cubed of 3x back, you got it correct. That's the by hand way of checking integrals, right? Take the derivative of your result, make sure it matches the integrand from the beginning. All right, so I'm going to enter this, all right, into the assignment, and we'll be done after an hour here with our first problem. Oops. All right. Pretty sure they'll want absolute values. So we got negative 1/6 times, and then I think we have to put tangent squared. Be absolutely certain. Trig. Now, I wonder if I can just put. No, I think you have to put the tangent in parentheses. So like tangent of 3x, and then that quantity squared. Although I can try tangent squared and then see if this works. I'm pretty sure this will work. All right, let's try this. So put the square where it usually is when you write it. I know technically it should be on the outside, but where it usually is, plus 1/3 times the natural log of, and then the absolute value symbols are here, right? And then you got secant x, and close those parentheses, and then again plus some constant. Don't forget for indefinite integrals, right? Plus some constant at the end. Let's see. Oh yeah, that's secant 3x. Double checking my paper here. I make sure I typed it correctly. So negative 1/6 tangent squared 3x plus 1/3 times the natural log of the absolute value of secant of 3x, then plus some constant. All right, then submit. Check it out. Great. Yeah, so they do have absolute values. They want you using absolute values, right, when you integrate and get a log. Wonderful. All right, and then again, they go through and every single problem you do, whether you get it right or wrong, has some answer explanation going with it. Please read through these, whether you're right or wrong. If you're correct, maybe you'll see some better way of doing it that they did that you like for future problems. If you're wrong, definitely see if you can figure out where you went wrong. And you'll see after all these problems in this homework here, they're just bringing back up what I showed you in the text, the strategy for, here it's powers of tangent and secant. And in the other objective, they'll bring up the strategy for powers of sine and cosine. All right, but yeah, highly recommend reading through the answer explanations. All right, okay, moving on finally to the next question. Okay, so here's another one with the powers of tangent and secant. All right, I'm going to do a little substitution for this one here so we don't have 4 pi x all the time and I have to write out 4 pi x all the time. All right, but yeah, so here we have, 2 pi times the tangent, to the 4th power of 4 pi x, and then times secant to the 6th power times of 4 pi x as well, dx. Let me write this out. Go through our strategy. Yes, I got the integral of 2 pi times tangent to the 4th power of 4 pi x, right, times secant to the 6th power of 4 pi x, and then, with respect to x. So yeah, like I said, I'm gonna call this 4 pi x, that's in both of these, theta, all right, or just e, or some other letter. I'll use theta. So I'm gonna let theta replace the 4 pi x. And so d theta, right, you also need to do differentials and integrals, when you replace them. So that'll just be 4 pi, right? 4 pi is a constant. So 4 pi times dx, right? So dx is 1 over 4 pi d theta. All right, so let me make these replacements. And I got the 2 pi here. It's going to be multiplied by 1 over 4 pi. So 2 pi over 4 pi, that's a half. And so I'm going to pull that half out. So I'll have half of, and then you have the tangent to the 4th power of just theta now, times secant to the 6th power of theta. And then again, dx was replaced by 1 over 4 pi d theta, and 2 pi over 4 pi was a half, right? So d theta. All right, so I have the case where, secant has an even power, right? And even powers of secant were easy. Well, you'll see. All right. Secants should be, easier. So I'm seeing this even power of secant here. So when you do that, you pull off 2 of them. So I got tangent to the 4th times, and then secant to the 6th. I'm going to peel off a pair, right? Make that secant to the 4th, and then times secant squared, right? That would be secant to the 6th. Okay, and then this secant to the 4th, I'm going to rewrite this so that involves tangent, and then we're going to make a substitution for tangent because the derivative of tangent is secant squared. So in terms of tangent, let's get that, right? In terms, that's secant to the 4th, I want in terms of tangent theta. Well, we got the half of the integral of tangent to the 4th powered theta. Now remember, secant to an even power. When it's an even power, you can take secant squared and raise it to some power, right? The power is a multiple of 2. So secant 4th would be secant squared, squared. I want secant squared involved because, secant squared I can rewrite as 1 plus tangent squared, or tangent squared plus 1. Right, so that's secant to the 4th, and then times secant squared theta d theta. And then here we go. I'm rewriting this secant squared here as 1 plus tangent squared. I'll do tangent squared plus 1. So we have half the integral of tangent to the 4th. And then secant squared, right, is 1. I just said out, right? Tangent squared plus 1. 1 plus tangent squared, same thing. That's secant squared in terms of tangent. And then that's being squared. Right, don't forget, it's squared squared, 4th power. Then times secant squared theta d theta. And now I make a u substitution. I'm going to let u be just tangent, not tangent squared, not tangent to the 4th, just tangent. And then du is this, the secant squared theta d theta, right? And the derivative of tangent was secant squared. And after making these substitutions, right, we got half the integral of u to the 4th, all right, call it just tangent to the 4th, u to the 4th. Sorry, shuffling papers. And then here we have tangent squared plus 1, u squared plus 1, but that's being squared, right? And then the rest of it, secant squared theta d theta, that's du. And now I have just basically a very, just a simple polynomial in u to integrate. But I do have to multiply it out though. This isn't super nice. So this is u to the fourth times, now when I square this would be u to the fourth plus 2u squared plus 1. And then when I multiply these two, we're getting this integral, the integral of u to the 8th plus 2u to the 6th plus u to the 4th, right? And then du. And that's easy to take, right? And then don't forget the half out here. Because, once you have a polynomial written as a sum, you could go term by term and integrate. So this is half of, and then 1/9 u to the 9th plus 2 over 7, right? 2 times 1/7 u to the 7th plus 1/5 u to the 5th. Okay, and then don't forget to sub back, right? The original integral was in x. Now here u was tangent theta, and remember from earlier, theta was 4 pi x, right? This was from earlier. So that means u is the tangent of 4 pi x. Okay, so that's going in here. Everywhere I see u, I'm going to rewrite it with the tangent of 4 pi x. And if I distribute the half here, we'll get the following. So 1/18th, right, half of 1/9 times, and then u to the 9th is this, right, the tangent to the 9th of 4 pi x plus half of 2/7 is 1/7, and then u to the 7th, right, u is the tangent of 4 pi x, so tangent to the 7th power, the tangent of 4 pi x to the 7th power. And then finally, half of 1/5 is 1/10, right, so plus 1/10. And then u to the 5th, tangent of 4 pi x to the 5th power, right, so tangent to the 5th of 4 pi x. And then again, for any indefinite integral, right, always plus some constant at the end. So yeah, this is, and again, you can double check you can check by taking the derivative of this and then trying to see if it's equal to what we started with. You might have to do a lot of trig identities and whatnot to check that they're equal, but so that might be a while. Or you can do the thing I showed you on Desmos, where you redefine, uh, you define the initial integral involving limits of integration, where the one limit is just x, and then you use a dummy variable t or whatever variable you like, and then graph this and see that they'd have the same shape and they're basically the same. They're the same thing, but possibly differing by some constant. Anyway, I'm going to enter this back on the assignment. So we got 1/18 times the tangent to the 9th of 4 pi x. So I got the pi symbol here. Oops. Next term, plus 1/7 times tangent to the 7th of 4 pi x. And then finally, plus 1/10 times tangent to the 5th of 4 pi x, not infinity x, pi x, slid on me. And then of course, don't forget indefinite integrals plus some constant plus c at the end. And let's just double check that what I typed there is what I wrote in my paper. Yeah, looks good. Submitted it. It's taken a while to check. These are some complicated things here, and there we go. Now, be aware, because these are trig functions, they might have a different answer than you, right? Because of trig identities. Now, if you're performing the strategy exactly as is, you're going to get the same answer they are. But if you see something different that you'd like to try, maybe some weird integration by parts or some other substitution you want to make. You might end up with something that's equally valid, but not exactly what they have, right? Um, these are trig functions. There's lots of trig identities. There's lots of ways to express certain functions in terms of others. So you may end up with an answer that's different than what they have, but as long as it's equivalent, they'll give it to you, right? As long as they are equal in some way, or some use of identities, they will give you the credit. All right, moving on. All right, so here I have powers of sine and cosine involved. So again, you can go back to the text or earlier in the video and look at the strategies there, and when you have powers of sine and cosine. All right. Okay, so this one's a multiple choice one, which is great. Because I don't really feel like going through all this every single time. It says, which of the following substitutions should be made to evaluate the following integral? All right, so I'll write it out and show you what I do to start it off. And following the same strategy that the book is laying out when we have even powers of both sine and cosine. So here's the integral. We have the integral of, I have in parentheses, negative 2 pi times the sine of x, but to the fourth power, right? Even power. This is multiplied by negative 4, and then times the cosine of x, right? But this is being squared. Right? Yeah. All right, so if I were to take the constant multiples out, right, negative 2 pi, negative 4, this would be positive 8 pi I would pull out, okay? Then times the integral of, sine to the fourth times cosine squared. All right, so here's a case where we're doing a product of sine and cosine, and they're both even. So if you recall, again, go back to earlier in the video or go to the text again. Remember when you're working with even powers of sine and cosine, you're going to use one of them power reduction formulas. So now the power reduction formulas were involving just squares. So I need to rewrite sine to the fourth here as sine squared, right? That sine to the fourth. And we have times, cosine squared. Okay, now that I have sine squared involved and cosine squared involved, we're going to rewrite these with our power reduction formulas, right? And again, I brought those up earlier in the video. So sine squared of x, right, I'd rewrite that as half of 1 minus the cosine of 2x. And if you distribute the half, this would be half minus half of, cosine 2x. Okay, so that's the sine squared, but don't forget this is being squared again. All right, so I'd have to multiply this out, and then I'd see a cosine squared and do it again. All right, another power reducing formula. So that's this, and then cosine squared, right, times cosine squared is half of 1 plus the cosine of double the angle of 2x, right? And there, right? So yeah, so that's our power reducing formulas applied to this. And then of course dx out here. And that's all they want. Oh yeah, and if you were to distribute the half on this, it'd be 1/2, plus a half cosine 2x. That's all they're looking for. 'Cause, yeah, I'd have to multiply all this out, and then if I saw any powers of cosine that were even, I would do it again. Right, and then if there were odd powers of cosine, right, I'd have to go through my strategies for like every single term that results when we multiply these out. So they're being very kind to me and just saying what would be the first step, right? So yeah, so look here. Now they didn't multiply the -2 pi and -4, but see how they're replacing sine to the fourth with, half, well, 1/2 minus half cosine 2x and then squared. And then here replacing cosine squared with half plus half of cosine 2x. So I'd make those substitutions, I'd make those replacements, use the power reducing formulas there. And then we would go on. But that's all they want. All right, just if we were applying the strategy that was laid out. Again, you can see that in the answer explanation, right? Here's the strategy laid out, the three different cases. When you have, products of sines and cosines. All right. Okay, so here I have an odd power of sine. All right. And then just like earlier, just so I don't have to keep writing 5x, I'm going to replace that with theta or t or something else. All right. So we got the integral of pi multiplied by sine cubed of 5x. Right. Like I said, I'm gonna replace that 5x with theta, right? So then d theta would be 5 dx, right? So dx would be 1/5 d theta. So I'm going to pull out the pi over 5, because you have pi and then divided by 5, pi over 5, we'll pull that out. Integral of sine cubed, and then 5x is now theta, right? And again, I replaced dx with 1/5 d theta, so again, I got the fifth outside already. So sine cubed theta d theta. All right, so I actually did this one, earlier in the video, sine cubed. I didn't take it to the end though, I don't think. Maybe I did, I don't remember, it's been over an hour already. But remember, when you have an odd power of sine, pull one off. So this is pi over 5, integral sine squared theta, and then times sine to the first, right? Just pull one of those factors of sine off as its own factor, and then d theta. And now I'm going to rewrite sine squared here, this, using the Pythagorean identity as 1 minus cosine squared. And then we'll make a sub for cosine. Pi over 5, integral of, right? And this, again, this sine squared is 1 minus cosine squared theta. And then you have times, sine theta d theta, right? And sine theta d theta is the derivative of well, the opposite of the derivative of cosine, but I'm going to have u be cosine here, right? We're going to make a u sub. So now I have u be just cosine, not cosine squared, not 1 minus cosine squared, just cosine. And then du be negative sine theta d theta. All right, so this sine theta d theta is negative du. So I'll pull that negative outside, so we have negative pi over 5. And then it's just the integral of 1 minus u squared du. All right, because again, cosine was u. And so this is negative pi over 5 times, and then our antiderivative here, u minus 1/3 u cubed. And remember, u is cosine theta, and remember, I want to go back to x. Theta was 5x. So I'm going to replace all the u's in this with the cosine of 5x. All right, so when we're all said and done, I'm just going to take this up here to this blank spot. This integral is negative pi over 5, right, times the quantity u, which is cosine 5x, minus 1/3 times cosine cubed of 5x. And then, of course, after all that, plus any constant would work out as well, right? And I'll just type this. So we had negative pi over 5 times the quantity cosine of 5x minus 1/3 times cosine of 5x cubed, right? So cosine cubed of 5x, and then close all that off, and then plus c at the end, right? And this should be equivalent to what they have. Great. Yeah, they actually distributed the negative pi over 5, right? Wonderful. And read through the strategy every time, go or maybe just have that section of the OpenStax text up and have the strategy in front of you or in some other window that you can refer to over and over again. So back to tangent and secants. Now this time it's a definite integral, right? So my final value, will be a number, and they ask for an exact answer, right? So I can't just enter this in my calculator and, whatever decimal comes up, enter that, right? They want an exact answer. So no calculator work here. Now we can use a calculator to check our answer at the end, right? There's nothing wrong with that. Okay. But we have a definite integral. So I got now the integral from, x equals 0 to pi over 4 of, and this is how they have it written, it's negative 2 times, tangent cubed of x, and then multiplied by secant to the 5th power. Dx. All right. Now, the negative 2. All right, I'm just going to pull that out right away. Constant multiple. Integral from x equals 0 pi over 4. Now, when I remove the negative 2, see I have both odd powers of tangent and secant there. All right, so remember for odd power, if they're both odd, right, if they're both odd, pull one of each, put it with the dx, just one of each. So if I do one tangent, take one tangent away, you got tangent squared times. If I pull one of the secants to the end, I'll have secant to the 4th. All right, and then again, I'm pulling one secant and one tangent to the end. So I'll have times a secant times a tangent, and then, your dx here. The reason for this, right, this here at the end, this is the differential of secant, right? Remember the derivative of secant is secant tangent. So now I want to get this stuff in terms of secant so I can make a u sub. Now secant to the 4th already is secants. It's tangent squared that I need to rewrite in terms of secant. Right. And the way tangent squared, you can write that as, secant squared minus 1. So this is now negative 2, right? Integral from x equals 0 to pi over 4 of, secant squared x minus 1, right? This is tangent squared. And then times secant to the 4th. And then times this, secant tangent, secant x tangent x dx. Now comes the u sub, all right? And because we have a definite integral, when I make my u substitution here, I'm going to change the limits. All right, I'm going to change these from 0 to pi over 4. That way I don't have to go back to the original variable when I'm done. So, I'm going to let u be replacing just secant. All right, just secant x. And then du, right, is going to be secant x, tangent x, dx. And for the limits of integration, right, the lower limit, when x is 0, right, the secant of 0 is 1. So u equals 1 would be the lower limit. And the upper limit, right, so again, that's going to be the new lower limit. And then when x equals pi over 4, right, secant of pi over 4 is the square root of 2. So we'll go to u equals the square root of 2, right, for the new upper limit. All right, so I make these replacements. And we get this new definite integral in terms of u, and I change the limits, right, so I don't have to go back to x when I'm done. So we have negative 2 integral from u equals 1 to the square root of 2 now. And then this secant x, right, all that's u, so it's u squared minus 1 times u to the 4th. And then the rest of it, I know there's a secant there, but secant tangent dx is du. And now I just have a polynomial. Now I gotta distribute the u to the 4th, of course, get this to be a sum, but this should be a lot easier than what we started with. So u equals 1 to the square root of 2 of, u to the 6th minus u to the 4th du. So we got negative 2 times, and I can anti-differentiate this, no problem. 1/7 u to the 7th minus 1/5 u to the 5th. Right, and we're evaluating this from, I don't have to go back to x, right? We change the limits to u. U equals 1, the u equals the square root of 2, right? So I plug in the square root of 2, I plug in 1, and we'll subtract those values. So this is negative 2 times. Now, when I plug in the square root of 2, which is the same thing as 2 to the half, right? So I'm going to do that, all right? So we got 1/7 times, 2 to the half to the 7th. So that'd be 2 to the 7 halves. And when you multiply those powers, power to a power, you multiply the powers. Minus 1/5, and then times 2 to the half, to the 5th, that'd be 2 to the 5 halves. So there's the value at square root of 2, or 2 to the half of this thing in the box, and then minus, and then the value at 1, when I plug in 1, this is 1/7 minus 1/5. All right, and then all this. All right. Seriously, we can simplify this if we want, but I'm just going to enter this, as ugly as it looks. I'm going to enter this. All right. And in fact, let me go to Desmos and check that this value is indeed the integral we were given. All right. So back here, all right, I can check this value. We had I had negative 2, all right, times quantity, and then inside that quantity were two other quantities. The first one was 2 to the 7/5, or sorry, 2 to the 7 halves power. I'm just going to call that 3.5. 7 divided by 2. 2 to the 3.5 power divided by 7 minus, and then 2 to the 2.5 power, 2 to the 5 halves divided by 5. All right, so that was the value at the square root of 2 minus, and then the value at 1 was 1/7 minus 1/5. then close all the parentheses out. Cool. So we're getting negative, 1.084 blah, blah, blah. And let me enter the integral. Int integral from, 0 to pi, we just type pi over 4 of, and then they had, negative 2 times the tangent cubed of x times secant to the 5th of x dx. Oh, something is wrong here. What's wrong? Oh, okay, so they don't do higher powers in Desmos other than squared, so I gotta enter them this way. All right, so this is gonna be put the tangent in parentheses, and then raise that to the 3rd, and then do the same thing with the secant. Put the secant in parentheses, raised to the 5th, and look, they're the same value. All right, so the number I got is the correct number, so I'm going to enter that in the assignment. Now, again, you can you can simplify them if you want, but I'm just going to enter it the way we had it. So as long as it's equal to the correct value, they'll give it to me. So negative 2, in parentheses, and then parentheses again. And I'll just enter it the same way I did in Desmos, 2 raised to the 3.5 power, divided by 7, minus 2 raised to the 2.5 power, divided by 5, right? Close that inner set, minus, and then the quantity 1/7 minus 1/5. And then close that, close the big one. And that should be good. Just make sure I double check everything. Make sure I typed in the correct numbers. It should be good. Yeah. All right. Now they completely simplified things with square roots and whatnot, but I got the same value. All right. And again, the strategy for tangents and secant products here. Power is a tangent, power is a secant. All right. So still some tangents and secants. This is pretty close to what we just saw, where you have odd powers of both again. All right, odd powers of both again. And the power on, the power on tangent is, yeah, they're both odd. All right, so write this down. So this should be pretty similar to the last question. So negative 2 pi times tangent to the 5th power of pi x, and then times secant cubed of pi x, and then dx. Once again, as I saw in a couple examples earlier in the video, I'm just going to call those theta, right? The thing inside the trig functions, those arguments of pi x. So I'm going to have theta be replacing the pi x, right? And then d theta would be pi dx, okay? So dx here would be 1 over pi d theta, and then negative 2 pi over pi would just be negative 2, right? So I'm pulling negative 2 out of this. And then now you'll have tangent to the 5th of theta times secant cubed of theta. Again, they both have odd powers. And then this will be d theta over here. They both have odd powers, right, over pi. Remember last example, right? This is the same thing in that strategy. They're both odd. Pull one of each. Pull one of each to the end. So I'll have tangent, to the 4th theta times, and then if I pull one of the secants away, you'll have secant squared theta, and then they'll be at the end. There's a secant I pulled away and a tangent, secant, tangent, tangent, secant, d theta, right? And the whole point of this is so we get secant tangent down here, and the derivative of secant was secant tangent, so I want everything else in terms of secant. Okay, so this here tangent to the fourth, right? That's tangent squared, and I can rewrite tangent squared as secant squared minus 1. And then I let u, sorry, I'm going to put all this in the same kind of line here. Then I let u be replaced with, replace secant. And then du is secant tangent d theta. Right, secant theta, tangent theta, d theta, which I'm seeing here. So that's du, and then this becomes u squared minus 1, and this becomes u squared. All right, so I'm getting this now. -2 times the integral, and if I distribute this u squared to the u squared minus 1, that's going to be u to the fourth minus u squared du, right? This is what I end up with after the u sub. Right. And so this is -2, and then times, 1/5 u to the fifth minus 1/3 u cubed. And then remember what u was. U is secant theta, or, going back to the original variable, secant of pi x, right? Because remember, theta was pi x. So finally, we have -2 times the quantity. You know what? I'll just distribute the -2. All right, so we get -2/5 times, u to the fifth, so secant to the fifth of pi x, and then -2 times -1/3 be plus 1/3, or plus 2/3, and then u cubed, secant cubed of pi x. And then, of course, after you're all said and done, plus, it's an indefinite integral plus any constant. So -2/5 secant to the fifth of pi x plus 2/3 secant cubed pi x plus some constant. So I'll go and enter that. -2/5 secant to the fifth of, pi x, and then plus 2/3 secant cubed of pi x. And then, of course, for an indefinite integral, plus c, plus any constant. Oh, what did I do? I must have rushed it too much. I am sorry. All right, let me go back to my paper, see what I messed up. My apologies. So I had tangent to the fifth of pi x, secant cube pi x, -2 pi dx. I let theta be pi x, so dx would be d theta over pi, making that -2, pulling that out. So then again, I pull the tangent away. You have tangent to the fourth, which would be tangent squared squared. Secant squared minus 1. You got secant squared, and then secant tangent. If u is secant, du would be secant tangent. That's u squared. Oh, yep, I know what I did wrong now. I forgot to square this. Remember I said tangent squared. This is tangent to the fourth. Tangent squared squared. So this, when I rewrite tangent squared as secant squared minus 1, that's got to be squared. And so I'll have u squared minus 1 squared, right, which would be u to the fourth minus 2u squared, and then plus 1. And then I'll distribute the u squared. All right, so my apologies, right? So I tried to rush things. See what happens when you try to rush things. Good lesson here. Maybe I shouldn't be rushing. All right, so what we have is -2 then times the integral. After multiplying each of these by u squared, right, we'd have u to the sixth minus 2u to the fourth plus u squared, right, du. And yeah, so this is -2 times, 1/7 u to the seventh minus 2/5 u to the fifth plus 1/3 u cubed Okay, and then I'm putting in secant of pi x for all these. And then, so we have negative 2/7, right? Distributing the negative 2 here. Negative 2/7 times secant to the 7th of pi x plus 4/5 secant to the 5th of pi x minus 2/3 secant cubed pi x and then plus some constant. So I'm going to go back and reshape this. My apologies again for forgetting that square. See, it's very easy to make one little tiny mistake and it throws everything off. All right, so negative 2/7. So give me another shot here. Times secant to the 7th of pi x. All right, of pi x. Close that. And we had plus 4/5, right? So plus 4/5 secant to the 5th of pi x. And then minus 2/3 secant cubed pi x. I just gotta change this last plus to a minus here, and there we go. This should be much, much better. Hooray. So that objective's complete. Wonderful. Again, be aware, be careful with, rushing things, right? You saw what happened this last example when I rushed, made a little boo-boo, right? Forgot to square something, and don't forget the strategy is recapped every single answer after every single answer. All right, so now we just got a bunch of sines and cosine problems left. All right. So again, remember the strategy. Now we didn't see every single case in the strategy with those tangents and secants, and I don't assume we're going to see every single case with the sines and cosines. Um, so, yeah, so if you ever come across something that we didn't cover here, you know, pull that OpenStax section 3.2 from the Calc 2 book up and, read through the part of the strategy that you'll need, and hopefully you can work it out. All right, and maybe I'll make some videos in the future where I go through each of those, but I just want to get through this assignment right now. All right, so let's write this out. Now this is a definite integral. All right, so my final value answer will be just some number. We have the integral from x equals negative 2 pi to 3 pi, positive 3 pi. And then the integrand is negative 3 pi times the cosine, to the 6th of x, and then times sine cubed. All right, so this is a nice one. Remember, when one of those is odd, when at least one of the sines or cosine is odd, it's very simple. Oh, it's relatively simple. I don't know if you're going to say it's very simple, but I'd say it's relatively simple. Okay. So yeah, when one of these is odd, like I got here with the sines and cosines, remember the strategy is just pull one of them off to the end. All right, this negative 3 pi I'm going to pull out. Actually, I'm going to pull out 3 pi and put the negative with the sign I put, because remember the derivative of cosine is negative sine, and I'm going to be doing a u sub for cosine here. You'll see in a second. So I'm going to just pull 3 pi out, just 3 pi. We have x equals negative 2 pi to 3 pi. And then you have cosine to the 6th times, and if I pull one of the sines to the end, you'll have sine squared. And I'm pulling one of the sines to the end, but also with this negative sign. Okay, so times negative sine x dx at the end here. And again, the whole point of this is because the derivative of cosine is negative sine x, and times dx if you're doing the differential. So what I'd like is all the rest of it to be in terms of cosine. All right, so I'm going to make this sine squared, rewrite that as 1 minus cosine squared. All right, I'm not going to rush this here like I did last time. And then I'm going to let u be cosine x, right? Just cosine x. And then du will be negative sine x dx, right? So this, right, negative sine x dx, that's going to be du. This cosine x to the 6th is going to be u to the 6th. And then this 1 minus cosine squared is 1 minus u squared. And that's not being squared or anything. This wasn't sine to the fourth, so it's just 1 minus u squared. And then I shall distribute the u to the sixth. We can also change the limits. All right, so the lower limit was x equals negative 2 pi. Cosine of negative 2 pi is 1. And the upper limit, right, is x equals 3 pi. Cosine of 3 pi is negative 1. So maybe that's why they had the minus there, because like when I rewrite this, we have a 3 pi integral from, again, this is the lower limit. I know it's the larger number, but remember the original lower limit was negative 2 pi. Plug that in. Cosine of negative 2 pi is 1. So that's the lower limit from u equals 1 and then to negative 1. Now, if you want to switch them, get the lower number on bottom, right, you got to make it take the opposite, right? Do negative 3 pi, and then you have, the opposite integral, and then you can switch the limits. And then after all this u substitution here, we have, u to the sixth minus u to the eighth, and then du. And yeah, if I want to, right, if you like having the lower number on bottom, which I do prefer, do the opposite. Now multiply this thing by negative 1, which will make this u to the 8th minus u to the 6th, right? Just do the opposite of the integrand there. And now we're going from u equals negative 1 to positive 1, right? That'll switch the limits if you do the opposite integral. Okay, so we got 3 pi times, antiderivative's easy enough, right? 1/9 u to the 9th minus 1/7 u to the 7th. And really, it's just going to be 1/9 minus 1/7 twice, all right? Because we're going, we could have also said this is even, go from 0 to 1 and double it, and whatever. I'm not going to worry about all that right now. I've already done the writing. When I plug these things in, all right, you're going to have 3 pi times, and then, when I plug in 1, it's going to be 1/9 minus 1/7, and then subtract. And then when I plug in negative 1, this will be negative 1/9 plus 1/7. But after distributing this negative, you can see it's 2/9 minus 2/7, right? So I'm just going to put that in 3 pi times and then 2/9 minus 2/7, right? Or you could pull the 2 out and make it 6 pi times 1/9 minus 1/7, whatever. This is it. I'm going to type that in. Now you can get the fractions together, get a common denominator, but as you saw in earlier examples, right, with the definite integrals, if I just enter something that's equivalent to the correct answer, they're going to give it to me. Of course, on a test or something, I would have you totally simplify, but this isn't a test. All right. So 3 pi times the quantity, 2/9 minus 2/7. Again, double check my work. Make sure I typed everything correctly. This should be good. All right. Yeah, negative 4/21 pi. All right, negative 4 pi over 21. Okay. Moving on. So another definite integral with some powers of sine and cosine. Right. I'll write this out. So we got the integral from x equals negative 2 pi to 8 pi over 3 of negative 3 pi times the sine squared, right? Sine of 2x squared times cosine of 2x squared. All right. And then dx. So look, this is one of those where both powers of the sine and cosine are even, When both of them are even, if you're following the strategy to a T, you're going to be using those power reduction formulas. All right. Now me personally, right, like I said before, with most of these problems, right, since both of these are 2x, just call it theta, and then d theta going to be 2 dx. And I can also change the limits as I go, right? This is a definite integral. So the lower limit, upper limit, the lower limit will be theta equals, when x equals negative 2 pi, theta would be negative 4 pi. Right, 2 times negative 2 pi. And then the upper limit, when x equals 8 pi over 3, this would be 16 pi over 3, right? Just doubling that. Right. And then dx, right, would be half d theta. So pull out this negative 3 pi. I'd have a half with that. Okay, so this would be negative 3 pi over 2 pulled out. And we got the integral from theta equals negative 4 pi to 16 pi over 3, right? I changed the limits. That way I don't have to go back to x. And then we have sine squared x, or theta, sorry, 2x is now theta, times cosine squared theta, d theta, right? Dx was d theta over 2. So here come the power reducing formulas. So negative 3 pi over 2, integral from theta equals negative 4 pi to 16 pi over 3. And then sine squared is half of 1 minus cosine of 2, double this angle, right? 2 theta. Now if I left that as 2x, this would be 4x, right? But I didn't. Times, and then same thing, cosine squared, right? Using half angle, would be half of 1 plus the cosine of 2 theta, right? And then we got the d theta here. Now notice there's a half times a half. So that's a quarter. I can pull that out. So negative 3 pi over 2 times a quarter would be negative 3 pi over 8. And I got the integral from theta equals negative 4 pi to 8 pi over 16 pi over 3. And then when you multiply these things, right, again, you got to multiply this out and possibly have to do power reducing again, right? Trying to take everything down to be the first power. When I multiply 1 minus, a minus b times a plus b is a difference of squares, a squared minus b squared. So this ends up being 1 minus cosine squared of 2 theta, right, and then d theta, which, I could write this as, that's for less, right, and this is the same thing as sine squared of 2 theta, right? 1 minus cosine squared of something is sine squared of that thing. And then I still have an even power of sine, so I got to do power reducing again. Now you could have done the power reducing to cosine squared, but I changed this thing 1 minus cosine squared to sine squared, and then I'll do the power reducing again. This is negative 3 pi over 8 times the integral from theta equals negative 4 pi, 16 pi over 3 of, and then, again, this is sine squared theta, 2 theta, so it'd be half of the quantity 1 minus the cosine of double that, which would be 4 theta. But notice it's cosine of the first now, right? D theta. And I can pull this other half out now. So this is negative 3 pi over 16 times the integral from negative 4 pi, I'm not doing subs, so negative 4 pi to 16 pi over 3 for theta of just 1 minus cosine 4 theta, all right, d theta. And I should know how to do, cosine to the first power of some linear expression. So here's negative 3 pi over 16. And then integral of 1 d theta would just be theta. And then, the integral of cosine is sine, right? So minus the sine of 4 theta, but don't forget that's 4 theta in there, so I got to multiply by a quarter to undo that, right? With the undo the chain rule, you'd be multiplying by 4 when you take the derivative. And we're going from negative 4 pi for theta to 16 pi over 3, all right, for theta. Okay. All right, so let's put this stuff in. Again, I'm probably just going to enter this the way it is when I'm done, but this would be negative 3 pi over 16. Now the value of this, when theta is 16 pi over 3, right, you'd have 16 pi over 3 minus, 1/4 times the sine of, 4 times 16 pi over 3. That'd be, a 64 pi over 3. Okay, which is, that's a lot, right? That's 21 pi, right? So an odd multiple of pi, and then plus another pi over 3. So remember the sine of pi over 3, right, was square root of 3 over 2. But if you were to draw this angle in standard position, that would end up in quadrant 3. This would be negative square root of 3 over 2. All right, sine of 64 pi over 3, or 21. Right, that's 21 and 1/3 pi, 21 pi plus pi over 3. Yeah. All right, so yeah, so that's negative square root of 3 over 2 there, and all right. Like I said, I'm just going to type this out as is probably when I'm done without simplifying too much. Minus, and then when I plug in negative 4 pi for theta, right, this is negative 4 pi there, and then, minus a quarter times the sine of, negative 16 pi, which is nice. And then all that. Because the sine of any even multiple of pi, or any multiple of pi for that matter, is 0. So that gets rid of that term. So I guess I could do a little simplifying. Negative 3 pi over 16. And this here is, 16 pi over 3. And then minus a quarter times negative square root of 3 over 2 would be positive square root of 3 over 8. And then you have minus negative 4 pi, so plus 4 pi over here, and that would be it. And if I were to distribute this, that would make this nice, But, I'll just leave it like this. I'll just leave it like this. Okay, I'm going to enter that. Yeah. All right. So negative 3 pi over 16. All right, this times the quantity 16 pi over 3 plus the square root of 3 over 8, square root of 3, and then divided by 8, and make sure the 8 is not in the square root there, and then plus 4 pi. Right, and close that big quantity. This should be good. Yeah. Right, and again, they rewrote it in a simpler fashion, but what I have is equivalent. Great. So again, there we had two, that's what you got to do with that power reducing formula, right? You got to do maybe multiple times when the powers of sine and cosine are all even. All right, moving on. So another definite integral, right? So we should end up with some value, some number. This time I have just a straight up odd power of cosine. Remember, if one of the powers on sine or cosine, if one of them's odd, like this one is, you have cosine to the fifth. Should be relatively simple. Just peel that one of them off, and take the even power and rewrite it in terms of sine. Right? Peel a cosine off, write in terms of sine, or peel a sine off and write in terms of cosine, and then make a substitution. So let's go through here, back to the paper. So we got the integral from, we're starting with x here. I might change this again. So x equals negative pi over 2 to x equals 0. 4 times cosine, to the fifth. Cosine of 3x to the fifth power dx. All right, so like I usually do, right, I've done this with several examples now. I particularly like having just a single, just theta in there. All right, so I'm going to have theta replace 3x again. And then, of course, you got to have your differential. D theta would be 3 dx. Okay, so dx is 1/3 d theta. And then for the limits, right, because it's a definite integral, I'm also going to change the limit so I don't have to substitute back. All right, the lower limit and the upper limit. Lower limit was originally x equals negative pi over 2. Now it's going to be negative 3 pi over 2, right? I'm just tripling those limits. Just triple the limits. Right, the upper limit's still 0, right? 3 times 0. All right, so after making these replacements, you got this factor of 4 here, and then I also have the third when I replace dx with 1/3 d theta. So I'm going to pull the 4/3 out. All right, so you got 4/3 times the integral from, now it's theta. Theta equals negative 3 pi over 2 to 0. All right, new limits of cosine to the fifth of theta. Remember, when it's an odd power of sine, odd power of cosine, pull one of them off. So I'm going to make this cosine to the fourth times cosine to the first, d theta. Again, dx is replaced by d theta over 3. And then this cosine theta d theta, right, that's going to be the differential of sine of theta. So I want to rewrite the cosine to the fourth in terms of sine of theta. All right, so remember this, cosine to the fourth. In order to write in terms of sine, though, I need cosine squared. So cosine to the fourth is actually cosine squared, right? And so this is, and then cosine squared is 1 minus sine squared. All right, so this is 1 minus sine squared, squared. And I forgot this square in a problem earlier in the video, right? So looking back at that, it was with tangents and secants, but all right, but now I make another sub. I let u be sine. Say let u be the sine of theta, right? And then du is going to be my cosine theta d theta. All right, so this becomes du, and then this here is the quantity 1 minus u squared squared, which, when I multiply that out, would be 1 minus, 2u squared plus u to the fourth, right? I'm going to write it out this way, so it's actually easy to integrate. So I'll have this du. And then the limits, right? I can do the limits again. Lower limit, upper limit. The original lower limit was theta equals negative 3 pi over 2. The sine of negative 3 pi over 2 would be the same as sine of pi over 2. That's 1. So u equals 1 is the new lower limit. And then the sine of 0, right, the upper limit. Sine of 0 is 0. U equals 0 is the upper limit. So it's 1 to 0. 1 on the bottom, 0 on the top. If you want to switch the limits, right, just do the opposite integral, multiply by negative 1. So yeah, so after making these replacements, all right, now we're in an integral with u. All right, so this is 4/3 integral from, u equals 1 to 0. All right, the new lower limit is 1, upper limit 0, of this, 1 minus 2u squared plus u to the fourth du, which I can easily do. Now, if you don't like again, me personally, I said this earlier in the video, I like having the lower numbers on bottom. Let's see, it feels more comfortable. So I'm going to do the opposite of the integrand here. We got 4/3 then. Multiply this by -1/4 times the integral from u equals 0 to 1 of, the opposite of this, which would be negative u to the fourth, plus 2u squared minus 1. I'm just putting in descending order. So here we go. 4/3. Use the antiderivative now, right? Polynomial. -1/5 u to the fifth plus 2/3 u to the third and minus u. And we're going from u equals 0 to u equals 1. And nice thing is when I plug in 0, that's nothing. So really this is just what's the value at 1, right? The value at 1 minus the value at 0, but the value at 0 is 0. So it's just 4/3 times, the value of this thing at 1 should be -1/5 plus 2/3 minus 1, which I'm going to type that in. I know you could pretty easily simplify that, but there's our value. I'm just going to type that in. So 4/3 times the quantity, we had -1/5 plus 2/3 and then minus 1 all in the parentheses there. Great. And it's that would simplify to -32/45, right, if you actually took the time. All right. I think, no, there's still one more. All right. Continue on. All right, so this should be the last one here based on the progress I've been making. Hopefully it's the last one. And once again, all right, you have odd powers. You have some odd powers. So an odd power on sine, odd power on cosine. So yeah, just take one of these, peel one of them off, pull one of them to the end, and then take the thing that's left over and rewrite it in terms of the other one, right? So you could pull a sine off and then rewrite sine to the sixth in terms of cosine, but that would be, sine squared cubed. So I'd have 1 minus cosine squared cubed and 1 minus u squared if I made a u substitution cubed. I don't want to multiply all that out. I don't want to cube something. So I think it'd be easier here to take the lower power, cosine cubed, pull a cosine to the end, and then rewrite cosine squared in terms of sine as just 1 minus sine squared, and that'll be easier. All right, so again, either way you do it, right, as long as one of these is odd, you can go through it. Right. And I also feel bad because we've gone through all these problems, secants and tangents, sines and cosines, and we never came across an odd power of secant that I could use this reduction formula for. I just wanted to bring that back up again because that's beautiful. But it doesn't look like I'm going to be using it for any of the questions that were thrown at me. All right, remember the questions you see might be different. So if you do come across some sort of integral of just an odd power of secant on its own, I might have to do, some sort of a reduction formula. Anyway, this here with the sines and cosines. We got the integral of 3 pi cosine, to the third power of 5 pi x times sine to the seventh power of, 5 pi x dx. So again, I don't like the whole 5 pi x in here. You can leave it if you want, but call that theta again. So I'm going to have theta be 5 pi x. And so d theta is 5 pi dx, right? So that means that dx is 1 over 5 pi times d theta. And when I make these replacements, right, you'd have 3 pi times 1 over 5 pi d theta, so that's 3/5 d theta, pull the 3/5 out. So I got 3/5 integral of the cosine of theta cubed times the sine of theta to the 7th and then d theta. So I like looking at that better without all the 5 pi's everywhere. All right. Now, because this is an indefinite integral, though, we'll eventually have to go back and put this 5 pi x back in for theta. So yeah, I got this odd power on cosine. I'm going to do this. Make this cosine squared, right? Just pull one of them off. And then you have sine to the 7th. And I'm putting that one cosine factor I pulled off at the end here. Right, so this cosine theta d theta, right? That's the derivative of sine. So I want to write this in terms of sine. So that's cosine squared, right? When I rewrite that in terms of sine, that's just 1 minus sine squared. All right, and then I make a u sub for sine. I replace sine. Let u be just the sine of theta, right? Then du is cosine theta d theta. All right, so that's this. That's du. And then this here becomes 1 minus u squared, right? And it's not being raised to any powers. And then this sine to the 7th is just be u to the 7th, and I distribute that over the 1 minus u squared. So we now have 3/5 times the integral of u to the 7th minus u to the 9th. And then, du. So it'd be 3/5 times, 1/8 u to the 8th minus 1/10 u to the 10th. And then we got to sub back, and I'll distribute the 3/5 as well. Now remember, u is the sine of theta, but theta was this 5 pi x. So u is going to be the sine of 5 pi x, right? So after distributing the 3/5 here, that'd be 3/40 times the sine, to the 8th power, the sine of 5 pi x to the 8th power minus, and then 3/50 times, and then the sine of 5 pi x to the 10th power. And then, of course, plus some constant at the end. Now, if you did it the other way around, if you pulled a sine off and had sine theta d theta, you would have had sine to the 6th power, which you would then have to have written as cosine, 1 minus cosine, sine squared cubed. And then sine squared cubed would be 1 minus cosine squared cubed. And then you make a u sub for cosine, and then you'd have, u squared for this, and then 1 minus u squared cubed, and, you'd get some crazy long polynomial, polynomial with 4 terms. That's not crazy long, but, so you'd get a different answer, right? You'd get an answer, it would be equivalent to this, but with cosines instead. That's all. All right. Yeah, so I picked the lower of the 2 odd powers because I felt like that would be easier. All right, let me type this in. And that should do it for this assignment. So we got 3/40 times the sine, to the 8th power of 5 pi x minus 3/50 times sine to the 10th power of 5 pi x. And then, of course, at the end, right, indefinite integral plus some constant. Great. Yeah, and that's exactly what they got. Again, if you pulled off the sine and did it the other way, yeah, see, if you did it the other way with the cosines, you'd end up with this 4-term expression, plus some constant. They explain, if you tried it that way first, the other way, you end up with this. All right. Oh, looks like we got one more. All right, I thought we'd be finished there. All right, so one more. So again, I have an odd power on sine. I got an odd power on one of them. As long as there's an odd power on one of the sines or cosines, right, just peel one off. and then write everything else in terms, if I'm going to peel a sine off and then write everything else in terms of cosine and then make a u substitution for cosine. All right. So one more here. Integral -2 pi cosine of pi x to the 4th power times the sine of pi x to the 5th power dx. So once again, I'm going to have theta, instead of pi x in here and in here, I'm going to have theta be pi x, right? And then d theta would be pi dx. So then dx would be 1 over pi d theta, okay? And then if I have 1 over pi times -2 pi, right, that's -2. Now I'm just going to pull the 2 out, and again, you'll see why. Instead of pulling -2 out, I'm going to pull 2 out and put the negative sign with the sign that I put over. I got cosine to the 4th of theta now. And then this sine to the 5th, I'm going to write as sine to the 4th times sine, but you know where that negative sign's going? I'm putting it here. So times negative sine theta, and then d theta, right? And this negative sine theta d theta, that's the derivative of cosine, or the differential of cosine. So I rewrite this stuff in terms of cosine. Now, cosine to the 4th is already good. Sine to the 4th, though, I need sine squared if I want to write things in terms of cosine. So this is sine squared, which in terms of cosine, that would be 1 minus cosine squared. Don't forget the square like I did that one problem about an hour ago. Okay, now the substitution. I'll let u be replaced by cosine theta, right? And then du be negative sine theta d theta. And that's this. There's du. This cosine to the 4th, right? That would be u to the 4th. And then 1 minus cosine squared, that'd be 1 minus u squared. And then 1 minus u squared would be 1 minus 2u squared plus u to the 4th, right? And then I'm distributing the u to the 4th. So we'll get the following polynomial integral. Okay, so this will be 2 times the integral of, u to the 4th minus 2u to the 6th, and then plus u to the 8th du. And this should be an easy one. So 2 times 1/5 u to the 5th minus 2/7 u to the 7th plus 1/9 u to the 9th. And then I replace u with cosine theta, but remember theta was pi x. So u is going to be the cosine of pi x. And I'll distribute the 2. So this will be 2/5 times, u to the 5th, so cosine of pi x to the 5th minus, and then 4/7 times u to the 7th, so cosine of pi x to the 7th, and then plus 2/9, right? Times, and then u to the 9th, the cosine of pi x to the 9th, and then as always with these indefinite integrals, after you're finished, right, plus any constant into this. Alrighty, so 2/5 times cosine to the 5th of pi x minus 4/7 times cosine to the 7th of pi x, and then finally plus 2/9 cosine to the 9th of pi x. And then don't forget, right, they will mark you down. It won't be right. Plus some constant for an indefinite integral. Great. Alrighty, and that, there, yay, I'm done. All right. So yeah, so again, after every single one of these, you got the strategy brought up again. Don't forget, right? You can always pull up section 3.2, trigonometric integrals. This is openstacks.org. Their Calculus 2, Volume 2 book, section 3.2 or 3-2. You got your strategy for integrating powers of tangent and secant. Then earlier in the text, your strategy for powers of sine and cosine that I was using throughout the assignment problems. All right. So yeah, let's continue and see that it's complete. Wonderful. And then as I say at the top of the video, right, I didn't see every possible case here. All right, you saw I showed you what happens if you have odd powers of secant, right? Near in the first like half an hour, 45 minutes of the video, when I was going over strategies. You didn't see that here. All right. So just know that that might come up. All right. I say it every time I make these Newton Alta videos, right? The questions I see here may not be the same as the questions you're seeing when you're working on them on your own. But I'm hoping that, watching me go through these, point out the strategies, help you enough, to make it a little easier for you when you work on the assignment yourself. All right, and thank you very much for watching.